J.J. Thomson continued to call them corpuscles for many, many, many years after everyone else called them electrons, but I'm sure no one minded because he did in fact discover them. And he was actually able to find out more than just that these were charged. From classical electromagnetism, he could actually relate the degree of deflection that he saw to the charge and the mass of the particles. So using that, he could say that delta x, and we'll put sub-negative because we know now that these are negative particles, is proportional to the charge on that particle over m, which is the mass. So we have E being equal to the charge of the negative particles, and m, of course, is equal to the mass of those particles. So Thomson didn't stop here. He actually continued experimenting with different voltages. And what he found was if he really, really ramped the voltage up between those two plates, he could actually detect something else. And what he could detect here is that there's this little spot of luminescence that he could see on the screen that was barely deflected at all. Certainly in comparison to how strongly this first particle was deflected, the second particle was deflected almost not at all. But what he could tell from the fact that there was a second particle at all and the fact that it was in this direction is that in addition to his negative particle, he also, of course, had a positive particle that was within this stream of rays that were coming out. So, of course, he can use the same relationship for the positive particle. So delta x now of the positive is proportional to the charge on the positive particle all over the mass of the positive particle. So this is interesting for several reasons. What did he manage to pull out information-wise from using these two relationships? And actually, to do this, he made a few more observations. The first, which I just stated, is that the deflection of that negative particle was just far and away more extreme, much, much larger than that of the positive particle. The other assumption that he made here is that the charge on the two particles was equal. So how could he know that the charge on the two particles was equal? And actually, he couldn't exactly know it. It was a very good assumption that he made, and he could make the assumption because he, in fact, did know that what he started with was this hydrogen gas. So he was starting with hydrogen. If some negative particle was popping out from the hydrogen, then what he must be left with is H+. And since hydrogen itself is neutral, the H+ and the electron had to add up to be a neutral charge. So that means the charges of the two pieces, the positive and the negative particle, must be equal in terms of absolute charge. So using this relationship, he could then actually figure out, by knowing, which he knows, how much each of them were deflected, he could now try to think about whether or not he could make some relationship between the masses, between the mass of the positive and the negative particle. So this relationship he was looking at was starting with the deflection and the absolute distance that the particles were deflected. So what he could set that equal to is he knows what x is proportional to in terms of the negative particle. So that's just the absolute value of the charge over the mass of the negative particle. He could divide all of that by the absolute value of the charge of the positive particle all over the mass of the positive particle. And as we said, he made the assumption that those two charges were equal. So we can go ahead and cross those right out. So what that told him was if he knew the relationship between how far they were each displaced, he could also know something about the relationship of the two masses. So essentially, there was an inversely proportional relationship between how far the particles were displaced and what the mass of the two particles turned out to be. So because he, of course, observed that the negative particle traveled, it was deflected much, much further by those plates, what he could also assume and make the conclusion of is that the mass of that negative particle is actually larger or smaller? Much, much smaller, exactly, than the mass of the positive particle. So essentially what he found here is the relationship between the mass of an electron and the mass of the rest of the atom, the rest of the hydrogen atom there, which is an ion in this case. And in fact, it's so much smaller, it's close to 2,000 times smaller, that we can make the assumption that essentially the electrons take up no mass. I mean, they take up a teeny bit, but essentially when we're thinking about the setup of the atom, we don't have to account for them as using up a lot of the mass